Okay, so I hope anyone who's watching this is having a great day. It's been 4 years since I uploaded anything about this whole algebra forms thing, but I wanted to talk about Charles Muses' W numbers and how this particular notation happens to play with his W numbers. So I'm going to speak a little bit, sort of just as a quick refresher to why the notation looks like it does, and then I'll try and explain how these forms interact with Muses' W numbers in a way that might make sense. Okay, so in some ways we are reinventing the wheel, right? X squared here, it is x times x. This can be understood in a couple different ways, right? So I had some prior videos talking about upper and lower triangle numbers. So there's a relationship between those two. The upper triangle number is x squared plus x over 2. The lower triangle number is x squared minus x over 2, right? So when you add these two together, the half x cancels the x squared over 2 in each form adds together to get you back to the x squared. Another way to think about this is you can say that x squared is equal to x plus 2 of the lower triangles, right? And again, that kind of makes sense from a matrix perspective, where if you have an x by x matrix, you have x elements along the diagonal, and then you end up having the lower triangle your numbers on those off-diagonal elements, and when you add the diagonal back into one of those sides, you get the upper triangle, right? So again, this is not novel. If you're into math, this should all be sort of astoundingly basic in a way. But I think, hold with me, you'll be interested in where this goes. So quick reminder then of how this works. So again, I'm using what I call J forms for complex numbers. So 1 sort of looks like an L. If you rotate that L by 90 degrees, just like your normally what people call I does, or you get J, right? Rotate that again, you get to -1. Rotate it again, and you get to -J, right? Now, so another way of thinking about that is that J squared, so J times J is equal to -1, right? That would be one way of representing that. Now, because we talked about this, the way in which the square function operates with these triangle numbers, so J squared getting you to -1, there's a couple ways to think about it. One way you can represent it is in a vector form using this notation. So you start off with J, and then it turns out there's 2 steps, which will then take you to the vector of its square, which is -1. So those 2 steps would be down here. So this would be down triangle of J, would be half, -1/2, sorry, and -1/2 J. So similarly, you can add the up triangle and the down triangle of this element together, and that's sort of why those zeros are representing here, right? So those come together into the -1. So what are Muses' W numbers? Well, I'm going to make it even more complex by not using W. I'm going to use an up arrow to describe his W numbers. So up arrow times up arrow is up arrow squared, let's say. And what that actually equals is up arrow plus a -1, right? So I'm going to stick to this sort of notation that I've been using here for the algebra forms, but you can think about this as up arrow plus a -1, right? Oops. There we go. Right, so this is probably more of a traditional notation, but again, we're trying to use these form symbols here. Okay, so what's weird about this system is that, and there's a paper on the Lion Path website that goes into this, but basically your left and right multiplication don't perform the same way. So the cycle for this, it's oops, let me try and keep this in focus here. The cycle for this goes something like this. So 1 times up equals up. Up times up equals up minus 1, right? Up cubed, so up equals -1, actually, right? So then that times another up, so 4 ups, we'll use sort of a more traditional notation for this, equals down, which is minus up. And then multiplying the 2 again, up to the 5th, actually equals up, down. All right, so now you should start to notice what things are getting weird. Up to the 6th is back to 1. Right, so sort of like would have been called J or O numbers, or the cyclic polynomial, where you're using omega and omega squared as sort of 120 degrees around the complex plane. With muses W numbers, you get something like this. So 1 times up is up. Multiplied by up again, you get to up plus a -1. Multiply by up again, you get to -1. Multiply that by up again, you get to what we're calling down. Multiply that by up again, and you come to here. So up, down. And so you can see we've been left multiplying the entire time when we've been sort of running through this. It's sort of an unstated assumption. But that equals down plus 1. And you can go through the process here, down plus 1 times up. Okay, right, down plus up equals, we'll distribute, down plus up, right? So what we did here was take up, down, we multiplied up against that, and that got us back to 1, right? Because you can see, as it turns out, we can, if you want to expand this is equal to down plus 1 plus up. Those two cancel each other, and you're left with 1. All right, so it's super confusing the first time you start playing with this, and really the only way to make sure you know what you're doing to get the right answers is to break things down into a coordinate component, or a coordinate sort of a plus b up or a plus b down form, and then multiply things through. Okay, so what's interesting though is, so when you use these kind of representations, certain patterns start to emerge, right? So I mentioned here the normal cycle, for the up cycle, because there's 2 cycles. What you find out is when you left multiply by up, you're traveling in some kind of ellipse that goes in this direction. When you left multiply by down, you're traveling in an ellipse that goes in the other direction. Now this is all within the same sort of complex plane, right? So it's all 2-dimensional vectorized numbers, not terribly different from the complex numbers. But it just so happens that things get a little bit odd, right? So let me fill in the down cycle. So 1 times down is down, times down again is down squared, which is over here. So it's a mirrored from up squared. Multiply this by down, you get to -1. -1 times down, as you might expect, inverts it and gives you up. And then down times up gets you over here, down up, which is of course sort of the mirrored from the up down that we are hitting as sort of the 5th power of up. So here's the 5th power of down. And then if you multiply down again, so it would be down times down up in parentheses, sort of as a thing, that gets you back to 1, right? So again, I encourage you to look up Jens Koplinger, and I'm drawing a blank on his co-author's name, but they have a paper which addresses this. They're using W as the actual thing here instead of up down, so don't get confused by the difference in notation there. But then, so what you'll find, so other fun things, the square and triangle formulations still hold. So up triangles actually here, or triangle of up, excuse me, is minus 1/2 plus up, sort of in the coordinate system. And then down triangle of up is actually just minus 1/2, right? And that works out well because you go, in terms of sort of a vector translation, up triangle of up takes you here, down triangle of up is a translation, minus 1/2. So adding those two vectors together gets you back to up squared, just like you'd want it to. Same thing with the other, right, that's dealing with this. You can also use that second formula, x plus 2 down triangle of x. So to figure out how to get to up squared, you can take up plus 2 down triangle of x. So minus 1/2 minus 1/2, get you back to the square. Right, so that same kind of logic that we've pulled from just basic counting systems applies to these more anomalous vector systems. So this happens to be, it's a little sloppy, down triangle of the square of down, right? And then these 5 elements, you'll notice, so depending on what you multiply them by, they will rotate and maintain alignment within the plane, right? So so here we've taken up squared and multiplied that by down. So you start here. If you left multiply by down, takes you here. Up triangle of up multiplied by down on the left takes you here. Up multiplied by down on the left takes you here. Not a surprise. And then, so we filled in here now, so and we'd already talked about the fact that if you put down triangle multiplied by down up, that gets you back to 1. Right. So let me. So this was something done a while ago, trying to lay out some of these relationships. You can see that things are getting a little bit complicated, and there's probably some ways to streamline it. But to point out another row, so here's up squared multiplied by this down triangle of the square of down element. So if you multiply this element by each of the 5 elements in this row, you end up with these elements. Boop, boop, boop. There's some other interesting things where you can take the up triangle of down up, and that will take you here. So that's 2 up plus 1/2, I believe, sort of, yeah, in coordinate space. And generally speaking, what you find is that any representation you find on the upper half plane can be mirrored in the lower half plane just by switching all of the down and the ups for each other, right? So there is some interesting mirror symmetry that comes out of this kind of stuff too. Yeah. Oh, yeah, here's another one. So here's up squared multiplied by sort of the comparable elements in the lower row. Right, so you can see here that the down triangle of the square of up times up squared gets you here. Up squared times down gets you there. Up squared times the up triangle of down gets you there. And then over here is up squared. This is a right multiplication here for the up squared thing. So that's maybe a little confusing too. But yeah, please explore. There's something interesting here. I'm sure other people will be able to find more interesting ways of making these numbers do something, because there's certainly some application of these that people haven't figured out yet. And, if you doubt that, just remember imaginary numbers. That's how we have televisions and electrical engineering and all sorts of important physics. So I have a strong suspicion that there's some deeper physics that could fall out of understanding muses, very strange number systems better. And I haven't seen anything that captures so succinctly the way in which these numbers function. So anyway, I hope this is fun. Have a great day, everybody. Cheers.